is Rui Ma. I'm a PhD student from Worcester Polytechnic Institute, and I'm going to present about advantage and application of palladium membranes. As we know that syngas production and hydrogen separation has been a really mature technologies, and it's really important for energy and in chemical industries. However, it's really expensive elements for a lot of applications, and to intensify and enhancing these problems, enhancing these very mature technologies is really challenging, but it's also going to have a really tremendous improvement for the industry. And we know that as more and more regions and countries has implementing the carbon tax policy, the IGCC power plant integrated carbon gasification combined cycle has to integrate a carbon capture process in order to control the carbon dioxide emission. So to implement this process with a palladium membrane is a really promising process, because on the same time, when we are generating electricity, we generate hydrogen, and also we capture carbon dioxide in the same time. However, most of the study of palladium membrane stays at the lab scale. And to increase this, to scale up this model, it's still really challenging, and it's still really important to commercialize this process. The objective of my research would be stays at the scaling up of this process. And in our lab, we were able to assemble a pilot scale palladium membrane reactors with 7 membrane tubes and a shell. And each membrane tube has 150 centimeters square of surface area. And it can produce pure hydrogen with a high purity of 99.8%. Also, then we put this unit into a real syngas condition. So here is the process. The preheated gas comes into the inlet on the shell side, and then hydrogen is being depleted from the membrane side, from the shell side, and then collected from the tube side, which is the permeate side. And the unwanted gas is collected from the shell side, which is retentate side. And from this module, we are able to get a hydrogen permeance of 8.2 and a hydrogen recovery of 37%. In order to further study the optimization of this process and to provide some useful data for further scaling up, we designed another 3D computational fluid dynamics module, and we compared it with the experimental data, and it shows a really good agreement. So using this model, we studied the influence of Reynolds number, temperature, and operating pressure. And we got the results that the membrane reactor has the best performance under medium Reynolds number and high temperature and medium to high shell pressures. Besides, we also use this model to study the variation between each tubes. So from this figure, we can see that the middle tube has a lowest hydrogen flux. This is because of the competition effect with the outer circle membranes. And from the asymmetric model, we see that there is also a variation of hydrogen flux. This is because we have an outlet on the side of the shell side, so that makes it angular. So to further increase this further scale up this process, we have to try to decrease this variation. So in conclusion, we are able to generate a high robustness and excellent physical integrity of the membrane, which can produce hydrogen with a purity of 99.8% and a recovery of 37%. Also, the CFD simulation we generated shows a great agreement with the experiment and can be further used to optimize this process. And also, it provided data for further scaling up. And thank you for my lab mates, and thank you for your attention.
So our next